This is a video for Math 117, Section 2.5. We've already talked about piecewise functions, but now we want to consider the limits of piecewise functions. We have a new notation here. A minus means I'm going to A and looking to the left. So as x approaches A from the left is what this means. This one is as x approaches A from the right or from above in the x direction, from below for the negative in the y direction. And then the whole limit is if they both match, then the whole limit will be the same as the limit at either of these. If they don't match, then the whole limit does not exist. As you're working through these problems, you might find it a little bit annoying that the box pops up here. You can take a snipping tool and use your snipping tool and take a little screenshot so that you can look this more carefully. And I'll do that here. So as x goes to A from the left, here's A is equal to 3. So there's where I am. A is equal to 3. And as x goes to A from the left, I'm going this way. And that means my value is going to be, the y value is my limit. So my y value here is 3. So this will be 3 from the left. As x goes to A from above, that's this way. And it doesn't matter whether there's a hole there or not. But we're getting on this piece of the graph and going to A from the right. So it says A plus, that's A from the right. So my value there will be 5. Because they are not the same, then the limit will not exist. Number 2 asks us to do the same kind of analysis with a different function. Here we can see there's nothing that's a problem on this function at all. There's no jumps, no vertical asymptotes, no heavy oscillation. So there's no problems at all for the limit here. As x goes to 1, so A is equal to 1, as x goes to 1 from the left would be this side, and from the right would be this side. They're both going to the same place, so they both go to 2. Now this says, what's the y value? What would the y value be if there's an open circle at the end of it? What would the y value be is what they're asking for. So here the y value from both sides is 2. So the whole limit exists and is the same as both sides. For the next graph, we can see at a equals 0 we have a problem. There's a definite jump here. On one side it looks like it's going off to positive infinity, and on the other side it looks like it's going to 2 when a is equal to 0. So I'm interested in a is equal to 0. That's along here. So from the left, the minus, a minus, this says go to A and go to the left. So as x goes to A, as x approaches A, and either way, as x goes to A from below is another way you could write it, but it's below on the x-axis, so it means from this side. So as x goes to A, that's this way, that's from below, so that looks like 2, and as x goes to A from above, I'm on this graph and I'm going this direction. So if it says A minus, that means I'm not even interested in what's going on to the plus side. This is A minus. If it says A plus, I'm not interested in what's going on to the minus side. So I'm just interested in what's happening close to 0. So this is around 0 on this piece of the graph. So as x approaches A from the right, it would take me to positive infinity. Now I believe for yours, they're saying that if the limit doesn't exist, which it doesn't at positive infinity, they're asking you to put D and E, which is fine. But the better answer here would be that it does not exist because it's going off to infinity. So positive infinity would be a better answer. They will not accept that in WebAssign. When you take the test, you'll have a graph that has a bunch of strange features on it, kind of like this one. Could have a vertical asymptote on it too. And you'll have to analyze function values and limits. So this one says negative 3 from the right. Negative 3 is here. There is no left limit because you can't get there from this side of the graph. So the left limit does not exist. There's nothing here. Negative 3 from the right looks like we're going to positive 1. Because we'll be grabbing this piece here and going, we'll be getting onto this piece here and going towards 3. Negative 3, that is. So go to negative 3, go a little bit above, get on the graph and travel back to negative 3. And that's back to negative 3 for x. So it's saying what is y? LIM limit as x goes to negative 3 from the right of f of x is 1. For the next graph, they're asking us what happens as x goes to 0. And I want you to think, you're looking at both sides, so you're looking at one side, and it looks like it at 0, from the left, it's going to 2. And the it we're talking about is the y value, the f of x. What's happening on the graph to the y value as x approaches 0 from the left? So it looks like it's going to 2. On the right side, it also looks like it's going to 2. So as x approaches 0 from the right, it looks like we're going to 2. So the whole limit would be actually 2. It doesn't matter whether there's an open or closed circle here, because you really are just interested in where it looks like you're going there. So the whole limit here, going from the left, going from the right, they both approach 2. I want to look at this graph for just a few more minutes so that we can kind of analyze the whole thing. This is not considered a hole in the graph, this part right here. This is considered an endpoint. A hole in a graph looks like a bead on a wire. It's hanging from a wire on both sides. So this is a hole in the graph, and the limits do not have problems at holes because you can approach from both sides. So the limit here at this hole would be 2. So the limit as x goes to 2 from both sides, positive and negative, is going to be 2. At 4, we have a vertical asymptote. On the left side, the limit's fine. It's 3. But on the right side, the limit doesn't exist because it goes to infinity. My best answer for me would be infinity, but WebAssign requires D and E. We have a right limit for negative 3. We have a problem at 2. It's a hole. So if I talk about the problems on the graph, it's not defined before negative 3. We have a problem at 2. It has vertical asymptote at 4. And it looks like it keeps going after 6. This implies that it's going to keep going. The one-sided limits have the same rules as the both-sided limits because, of course, to do the whole limit, you have to go from both sides. But if we look at putting 1 in here, if it works, we're done. 8 minus 8 is going to give me 0. So the limit here would be 0. When I put 1 in here, I'm going to have 1 plus 5 or 1 plus 4. It works. No problem there. The problem for this graph would be a negative 4 because that's what would make the denominator 0, and we'd have a vertical asymptote there. But that's not where they asked for the limit. They asked for it at 1. For the next couple of problems, they're asking the same 1 over x, but they're asking for the limits from the left and the right. The right one first and then the left one. So let's put this on a calculator. So going to y equals, I'm going to put in 1 divided by x. I'm going to do a zoom 6 because I'm not sure where I was the last time. And I look at my limit, it looks like this. So going to 0 from the right, I knew there was a problem because x equals 0 in the denominator gives me 1 over 0, which is undefined. So if you don't know that 1 over 0 is undefined, you want to write that down and memorize it, because we definitely have a problem at 0 here. So from the right side, the limit is positive infinity. From the left side, the limit is negative infinity. In WebAssign, these would both be does not exist. So studying limits like this, if you put the number in and it works, you're done. So if I put 4 in here, I'm going to get 16 minus 16 plus 9. So I don't have a problem at 4. 16 minus 16 plus 9. No problem. So this is 9 in the denominator, and then 4 plus 5 would be 9 in the numerator. If I put 4 in here from above, that'd be okay, but 4 from below would not be, because 4 from below, from the negative, from the left, is not defined. So I want to look at that graph. So if they'd ask me for negative, then I'd have a problem here. 4 times second square root of x minus 4. Should have cleared that out first. It's one graph, and it looks like this. So see from the left on this graph, I can't find the limit because I can't get on a graph and actually travel there. But from the right, I can. It looks like it's 1, but that's not really true. So if I do a second table set, I'm going to put it at 4, because that's where I'm interested in the limit, and do a second table. sorry, I want to actually go here and do .0001. So I want it kind of close, and I'll do a second table and we'll see what that says. I can see it's defined at 4. So this is actually defined at 4. So don't just plug it in. If it works, you're done. If you have a radical or a denominator, because you've got some issues if you have a radical in particular. This one here says -4 from the positive side. So this is a little bit bigger than -4. So this one's going to work too, but you'll want to put it in and examine what that limit would be. If it had asked you -4 from the negative, from the left, this limit would not have existed because, again, it wouldn't have had a graph. This didn't have a graph before. When we go to find a limit like this, if I put the number in 8 and it doesn't work, we've got a 0 in the denominator, sometimes it means that I can factor the numerator and that factor will go away and I just have a hole in the graph. But in this particular case, 6 plus 8 in the numerator is going to give me something that's not 0. It gives me 14. So this would be 14 over 0. So for those kinds of limits, the limit does not exist. On this next one, you might want to put it in your calculator if you're not quite sure what to do here. But I can see that -2 from above is going to make me slightly bigger than the -2. So that means the numerator is going to be 0. The denominator doesn't have a problem. So if you can notice what the answer is right away, you won't need to put it in your calculator. Now we've looked at a lot of graphs of piecewise functions. So what does it look like when we're looking at the actual function? We have the description of the function here instead of the graph. So f of x is -x plus 9 below 0. That's to the left of 0. And to the right of 0 is 2x plus 3. So when we evaluate the limit, we're going to put this in. And these are both nice. They're both aligned. So if I put 0 in, I'm going to get 9 for the first one. That's from, oh, I put it in the wrong place. See that 0 plus? That 9 is not in the first one. It's in the second one. That is from below. Notice that the less than is pointing to the left. So 0 minus is to the left. So there's a nice little clue there for you already. 0 plus is going to be pointing in the positive direction, so it's to the right. So if I put 0 in this one, I get 3. Now I know if I graph this function that I've got a graph that has a jump in it, because at 0, the right side is 3 and the left side is 9. So if I wanted to find the whole limit here, it would be does not exist. The distinction between discontinuity and the limit not existing is that if there's a problem on the graph, the limit could exist if it's a hole. This one has a hole. But it's still discontinuous. There's definitely a problem there. So if you have a hole, a jump, a vertical asymptote, or a heavy oscillation, you will not have continuity on your graph. But here, this graph just has a hole in it. So we can see that the function value at 0 is actually 0. The limit is going to be 1 because as we go from the left and right there, we get 1. So as you're looking for points of discontinuity, you're looking for holes, jumps, vertical asymptotes, or heavy oscillation. This has a sharp corner on it, but that doesn't mean it's discontinuous there. So there's no problems on this graph. For this f of x, if you factor the numerator, the x plus 1 factors out. So there's definitely a hole in the graph because x plus 1 in the denominator means that the function is not defined at -1. But then the piece comes back, the second piece comes back and defines it there. So the f of x, just for the first piece, has a hole in it. And it's not plugged, it's not removed by putting the 1 there because the 1 is not actually the function value. So when I talk about discontinuity, the problems on the graph are going to occur if you're looking at functions like 27 and 26 here. If you have a denominator that is 0, or if you have negatives under the radical. Any other place, you're not going to have any problems on the graph. So here, this is just a polynomial. If you put this in your calculator, it's just a parabola. So everything looks fine on this. So this kind of function would be continuous everywhere. In 27, the denominator is never 0, so there's really not a problem here either. But you can graph it and take a look. If you have a rational function, the previous one didn't have a 0 in the denominator, but this one does have a place where it's equal to 0 in the denominator, so there's definitely no problem with this graph. This one here has two places, if you factor this, that there's a 0 in the denominator. For number 30, both of these pieces are nice. It's a line in the first one, it's a parabola in the second one, so they're defined everywhere. So unless they don't meet up, so when I put 0 in here and 0 in here, if they don't have the same value here, they're discontinuous there. But if the values are the same, they're continuous. You could put this in your calculator in Y1 and check to see that they actually do not match up. You probably are going to want to put 31 in your calculator. Let me show you where that absolute value is. So for the numerator, I'm going to need an absolute value, and there's two places to find it. In math, number, absolute value is there. Or you could go to second catalog, and it's the first one in the catalog. So y equals, I have the absolute value of x minus 13. It looks like it's going to cancel, but it doesn't. It's not just a hole in the graph. If it was x minus 13 over x minus 13, it would be 1 everywhere except for at 13. And then divided by, I need parentheses for the denominator. I didn't need them for the numerator because I put absolute values there. If you have a TI-83, you probably would have had to close the parentheses off for the absolute value in the numerator. Minus 13. And I graph this. Now this graph is from negative 10 to 10, so I'm not even seeing where the problem is on the graph. So I need to change my window so I can at least see where the problem is. So I'm going to go to maybe 15. If we graph, we can see now the jump in the graph. So using your calculator to help you see what the discontinuities are, you have to make sure that you include the place where the discontinuity is. And there's a problem at 13. They've already put the braces in, indicating you have a solution set here. They want you to separate your answers with a comma. So what makes this denominator 0 is going to be 4 and negative 4. Oftentimes when you have an x squared minus 16, you're thinking take the square root, you get 4, but you get a plus or minus 4 when you take the square root. So they didn't say any particular order, but I'll put it in the order of on the number line, and we have negative 4 and 4. On number 33, it's already factored for us, so we can see what the zeros are going to be there pretty easily. 9 will make this 0, 10 will make that 0. On number 34, you want to have all the values for which the function is discontinuous. So even if you factor the numerator on 34 and a factor cancels, you still have anything that's 0 in the denominator as a spot for discontinuity. It could just be a hole in the graph, could be a vertical asymptote. So all you're interested in here is what makes that denominator 0. You can factor out an x, you end up with a couple of factors. Number 35 says that Michael is solving problems correctly during a mathematics quiz, and y denotes the percent of the work completed, x is measured in minutes. Give it an interpretation of the graph. So, as we're starting the quiz, as Michael starts the quiz, it looks like he picks up the pace pretty well and he's doing pretty well. And right in here, it looks like he slowed down really badly and actually stopped working for a while. So for a few minutes, he stopped working. That happens to me sometimes when I'm in the middle of a problem and I can't quite figure out what the next step is. Sometimes people will call this part where you're not doing anything at all, they call that test anxiety. And that's really just you're doing something besides your test. If you can get your brain calmed down enough, you can get back to the test. And that's what happened somewhere in here. He stopped working for a while. Maybe he took a break and went to the restroom. And then came back, picked up the pace, jumped, and was suddenly able to get a lot of it done. So he was working on a problem, and suddenly he had the answer, jumped, and continued working until he finished the test. This is the graph of the amount of home heating oil remaining in a 200-gallon tank over a 120-day period. So looking at this graph, we can see that the tank was filled up, 200-gallon tank. We empty it out slowly, and then it's filled up again. We empty it out again, and this time we empty it out even more. And then it's filled up again, and we use it very quickly. That looks like a cold spell in there. We used it very quickly here. It went a lot steeper. And then it went so it warmed up a bit, and then we filled it up again and used it, filled it up again. So the steepest part, it looks like, might be in here. This looks like the coldest part of the heating cycle. Well, this is when we're using moisture. And it could be in here. This is pretty cold in here too. So we want to think about the steepness of these things too. So we're filling up the tank, emptying it out. It took us 40 days to empty it here. So we're looking over a period of 3 months, 4 months? 4-month period. So for which values of t is the function discontinuous? That's all I want to know. So you don't really have to understand the graph to be able to answer it. You can just about go blah, 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 blah. Where are the discontinuities? So you want to enter your answer as a comma-separated list. So we're going to put our numbers straight across here, everywhere where this graph is discontinuous. I don't know that they include the endpoints of 0 and 120, but if you don't get it right the first time, that might be what the problem is. Salesmen often get paid a monthly salary, and then they make commission based on how much more money they make for the company. So this one here says that the salesman is making $9,000, and then for each of 30,000 of sales beyond 100,000, he's paid an additional $1,000. So this says after 50,000, he gets paid an additional 50,000. So this could not be the graph. The second one says that if he makes more sales, then he's going to end up with a decreasing salary. The third one is if he makes 100,000 and 30 more, he jumps up 1,000. So that looks like for every 30,000, he's going to jump up another 1,000 in salary. And the last one says his salary continuously goes up. He starts at 0, and if he makes money, he actually gets paid that money. Now they want you to determine, once you have your list, exactly what the values are for x, for which the function f is discontinuous. So that just means where are every one of the jumps. So we're looking at the jumps here. Now it was 100 plus 30,000, and it's every 30,000 there's a problem. So just be careful when you're adding 30,000 here. It's been a little while since we played with the WebAssign graphing window, so let's kind of go through the steps again. You're going to pick either the line, the ray, or the segment. And each of these has an endpoint. The last one does not, however. So x is greater than 60, so that one you're going to need the ray. So for the first few, you're going to need the line, the segment. I'm going to go ahead and put all the segments on here. There's one segment. There's another segment. And I'll put another segment. And then I'll put the ray. So now I have all the features I need for my graph. For each of the segments, I need 2 endpoints. So in the first segment, I'm going to put in 0 and 10. So I get 0 and 90. So there's my first segment. And I need to decide whether it's open or closed. So both of these are open. Both open. And basically you know that because there's not an equals. So if there's not an equals, well, when there is an equals, it's closed. When there's not an equals on it, then it's open. For the last segment, I'll let you do the segment 2 and segment 3. But for the last segment, which is the ray, I need 2 points. And I definitely need the endpoint. So 60 I put in, and I got 435. 60 and 435. And I just need another point on here. So then I'll have to put in a different point. It doesn't matter, you could use 61, but I'm going to use 70. And I got 507.5. Now once you have your graph, well, just for a minute, the endpoint here, there's only one endpoint, and it's a greater than or equal to, so it's closed, so that looks good. It doesn't matter that there's another point on the graph because it's closed in, so that doesn't matter at all. Once you have this, you can analyze where your discontinuities are. Like I said, I'll leave the other segments to you. For numbers 39 and 40, you're trying to find a k that basically plugs the hole in the function, that causes these two pieces to come together and join, takes away the discontinuity. So I'm going to look at number 40. So if f of x equals to x squared minus 64 over x plus 8, where x is not equal to negative 8, and k where it is equals to negative 8, I want these two pieces to match, which means that I want, when I put in -8, so put in -8, and the two pieces have to match. So I have positive 64 minus 64 over -8 plus 8. This gives me 0 over 0, so that's not very helpful. So I can't just put that in. So if I look at this function again, so this didn't work. If it worked, I'd be able to do the procedure of just putting those two equal to each other, but I'm going to have to reduce it. So I have x squared minus 64 over x plus 8. That's the same as x plus 8 times x minus 8, over x plus 8. The x plus 8 goes away, and we're left with x minus 8. Now I can set x minus 8 equal to k, and I want this at x equals 8. Negative 8, sorry. And x equals -8, so I get -8 minus 8 equals k, which implies that k equals -16. So you may have to do a little algebra to figure those out. For the next kind of problem, we have the intermediate value theorem that says for f continuous on AB, so that means that from A to B, f looks pretty good. No discontinuities. So this is A, this is B. This would be f of A, and this would be f of B. So for every m in here, so m is in here, between f of A and f of B, there's a c. So if I pick an m, that means that I can draw a line across here, and there'll be a c in between A and B, such as f of c equals f of equals m. So that's the idea of what the intermediate value theorem is. Well, that's actually what it is. So looking at this one, I'm going to examine this on my calculator. So if I put this in my calculator, y equals, clear, x squared minus x plus 1, x squared minus x plus 1, and I want m is equal to 13. And I'll draw, because we're on the interval from -1 to 9, -1 to 9, I'm going to put in -1 to 9 and do a zoom fit. So there are several ways we're doing the intervals here, several ways we do the graphing, but for each one there's kind of a procedure, so you kind of want to see what you're looking at. If you're looking at an interval, that implies you want a certain x max and min, so you put those in. I can see the intersection here. We've already done the intersection. Second calc, intersect 5, enter. And we get that x equals 4. So for x equals 4, that's our c value. So the value c, f of x equals 13. F of 4 equals 13. So our answer would be 4 there. We used to use the method of bisection to determine roots of an equation. So you just keep trying numbers in, and all those numbers would be done by hand because you didn't have a calculator. So basically it means I'm going to try an interval and find something close to what will give me a true statement here when I put it in. So looking for the root of the equation, root is the same as the x-intercept or the 0 for the equation. So I'm going to do instead of doing the bisection method, we're going to find the 0 here by using our calculator. So in y equals, we're going to put x to the 5th plus 3x minus 9. And then I'm going to graph, and I see that my graph looks like this. I can see that I'm going to use between 1 and 2. Bisection method, we would try 1 and 2, and we'd see that 1 was less than 0 and 1 was greater than 0. And then we'd try the midpoint, 0.5, and we'd see which one was less than 0 and which one was greater than 0. And we'd decide whether we'd use the second or the left interval. Well, that's a lot of work when we can just with our calculator do second calc. We want a 0 because a root, a 0, and an x-intercept are the same. You might write those down for your notes because that concept isn't going away. So I want 2 is the 0. we want left bound, and here I can see it's between 1 and 2, so I can just put in 1 and 2, and notice that it's giving me cutoffs, and it's telling me now an interval that I'm trying to find the 0 between. So your calculator is actually doing a method of bisection to find the 0. It's what's programmed in to the algorithm to find the 0 on the calculator. It can't see, this calculator can't see where the 0 is. It can't just go find it and trace it. So I'm going to put a guess of maybe 1.5 because it looks pretty close to 1.5. Enter, and I got 1.3730. So I would think that the decimal accuracy they wanted here was 2 decimal places. So we would want this to be 1.37. Now it might be off one decimal here because they're expecting you to use the method of bisection. So it might be that it's a little bit off on that 1 decimal place. So you might have to try it twice.